Hello, everybody. I am Shadi. So we did our research in partnership with the National Cybersecurity Centrum in Netherlands. And it's part of Master of Security by the University of Amsterdam. So let's say our presentation will be divided into an introduction. Then we will introduce what's the problem and a little bit of a background about the AI and machine learning. And we will explain also the implementation for our approach and the results that we found and our conclusions for future research. So we think that this presentation is all about you. So we was wondering who knows about fingerprinting. And anybody worked with AI before? That's fair enough. So let me introduce the major problem. So malicious infrastructure is actually, we mean by that command and control servers. It's like Cobalt Strikes and Empire. And they use the port 80 HTTP because, you know, you can really easily hide things in it. So what we did is actually is a passive approach for how to find malicious infrastructure. And the reason because the partner that we worked with, the National Cybersecurity Center, you know, they don't do any active scanning, so they use open data sets to analyze any malicious IPs. And this is what actually we did is we took an open data set and we tried to analyze it, to analyze all of the HTTP GET requests for the root, for the whole IP version 4 space. Actually, what inspires our research is a previous finding by Fox IT, which they found actually a space in the header of Cobalt Strike command control servers, and they managed using this space to find all of the command and control servers. As we can see here from the photo, that the space is you know, it's barely recognizable. It's after the OK, and this is what identified a lot of Cobalt Strike's command and control servers. And we can see here, according to the statistics, after the finding that they managed actually to see that the half of the command and control servers on the internet are really Cobalt Strike. But after the batching, we see that a decreased number of command and control servers because this anomaly was patched in January 2019. But this explains really the importance of using such anomalies. Let me give you a quick introduction. We think that about for the people who didn't work with the command and control servers, what are they? They try to hide their message in HTTP, and mostly because most of the other ports are blocked by the firewalls. And it's also really hard to analyze all of the traffic on the HTTP because it's a really busy port. So, and what fingerprinting means is actually is only a technique used to identify this malicious CNC servers. But most of the ongoing research nowadays is all about anomaly detection, focusing on outgoing and incoming HTTP traffic. Of just one host or one network, but there is no research about how, you know, passive analyzing. So we thought, okay, let's introduce a passive fingerprinting only for the HTTP GET root, only by analyzing the responses that we get in an open data set. The advantage of this approach would be that the network still is not breached yet. So you're really trying to find and, you know, going step ahead before the network being compromised. So there is no active beacon. And actually, also you're not doing a lot of active scanning, which for some organizations like government will be illegal to do. So because we are searching for a really subtle anomalies to fingerprint, like space or something, and these anomalies are really subtle, we thought that machine learning can be a tool to be used to analyze and find these anomalies. And this is actually introduced our first research question. And that's what features can we extract from the HTTP responses? And we will explain what we mean by features later in the talk. But also because machine learning have a lot of techniques and have a lot of algorithms, and I am not actually, because Freek is the AI expert here, we thought, okay, maybe it's not going to work, that not all of the algorithms or all the technique in the machine learning can be used to detect anomalies in the HTTP responses. So this is introduced another research question. Okay, what is the best machine learning algorithm that you can use to find anomalies in HTTP responses?
Okay.
I will give the mic to Freek.
Yes. Hi, everybody. I'm Freek. So I will give a brief introduction into AI and machine learning, as we expected that maybe not everyone is so familiar with these techniques. So what machine learning, a definition I like about machine learning is it's learning through experience or data. So we have normal programs. They just, a programmer programs them, they work, and then nothing changes with what they learn themselves during the process. So machine learning needs a training before they are actually usable. And the two main techniques used in machine learning are supervised or unsupervised learning. Does it work? No, it doesn't. Okay, so I can tell you, and then So supervised learning. Supervised learning, the difference between supervised and unsupervised learning is the nature of the data. And so supervised learning uses labeled data. That means we have data points, and beforehand we already know if they are, in our case, command and control servers or not. So for this to work, we need a training set with labeled data, and then a testing set, which is a different part of the data set on which the algorithm, once it's learned and trained, can be tested to see the performance. And the tricky part for this research is that the creation of the data set would mean that command and control servers would have to be found and then put into the dataset labeled as command and control servers. And such datasets at the moment, they don't exist. So it's very hard to train and evaluate. And supervised learning really needs this labeled data, and usually a lot of it. So, and some of the examples of supervised learning techniques are regression models or support vector machines, and of course neural networks, which are used in deep learning and is a very hot topic right now. And unsupervised learning has the advantage that it doesn't need labeled data. You can throw all the data you want at it, and it tries to group data together. So that could mean that it's a better suited for this problem, as we have a lot of data, but we have no idea what we're actually specifically looking for. So a clustering algorithm can group the data itself. And two of the well-known clustering algorithms are k-means clustering or EM clustering. Let's see. Yes. Hey. So for our research, we needed to first transform the data. The problem is AI models, AI and training models. They need numbers. And HTTP responses, of course, they are not numbers, they are text. And for this, we needed to transform it, and the mechanisms that we used were the data that we transform. It's very different from other AI implementations. So, for example, feature extraction is very advanced in image processing and natural language processing, but our data, it is text just as natural language, but the problem is HTTP is very different in nature than books or tweets or other things, because it's very context dependent what words are there. So stuff like bag of words, which is the most used feature extraction technique in natural language processing, it doesn't really work for HTTP responses. What bag of words feature extraction is you just count every occurrence of a word in a text. So, for example, if you have a book, you would count all the different words, and on that you can then do analysis. Okay, these words are very common, and maybe they are not common in the normal corpus we would expect. And this is kind of the basics of how a lot of information retrieval in natural language was started. But in HTTP, most of the words, headers and values of headers, they are all only occurring once. So if you would put that in the matrix, then you would only have zeros and ones, and that loses a lot of potential and also needs a lot of storage to have, because there are a lot of different words possible, but they are occurring only once usually. So that's why we focused our research on defining new features, and we have defined two new features which can be used on HTTP headers specifically. So we, in the dataset of HTTP responses, we didn't really look at the bodies, but only at the headers, as most command and control servers, when you just throw a random HTTP GET request at them, they will give an error. So they will only give headers and maybe and not really an HTTP body. So that's why we focused on the headers. And the first feature we defined was the uniqueness features. And what we try to do with this feature is define a number, give a number to each HTTP response corresponding to how unique the combination of headers in the response are. And to do this, we have an algorithm with two steps. First, we needed to see, okay, which headers are frequent and which headers are not. So we counted all the header fields in the data set and looked at how common they were. And each specific header, so examples are connection, server, date, each header has its own uniqueness value. And the uniqueness value is 1 minus the header, the frequency of the header divided by the total responses. So as an example, we have here the connection header. The connection header is the most frequent header in our data set. It was in 95% of all the HTTP responses. So that means we give it a uniqueness value of 0.046, meaning it's not very unique. The higher the value, the uniquer the header is. And another example is an access control allow origin header. This is a very unique header. It's only in a bit over 1% of the data set. So it has a uniqueness value which is 0.98 instead of a very low uniqueness value which we see for the connection. And for all the headers that are in less than 1% of the data set, and there are a lot of very unique headers which only appear a few times, and to compute a different uniqueness value for all of them would be very expensive and wouldn't really change their value that much. So we gave them all the same 1% value, so 0.99. After we have all the uniqueness values for specific headers, we can compute uniqueness value for the actual HTTP response. So to do this, we add the uniqueness value of all the headers present. So if there are 4 headers, we add the uniqueness value of those 4 headers. So if there are very unique ones, this will be higher, and if there are if the unique ones are missing, then this will be lower. And what we also do is add the inverse uniqueness for the headers that are absent, because if the connection header is absent, that would mean it is a more unique HTTP response than if the connection value is actually there. So this later we will show the results of this uniqueness feature, and Shadi will also go more into the implementation. The second header feature we have is the ordering. And the ordering is actually quite simple. So we chose to analyze the 5 most common headers and see in which order they appear. So here's an example where you see the server is first and content type is another common header which is after that. And in this way we can define an ordering of the most common headers. The only tricky part about this is partial orderings. Meaning, okay, what if some of the headers are missing and others are not? For example, if we have one HTTP response which has a server field and a content type field, and after that a content length, while another HTTP response does have the server first and content length after that, but no content type, then the ordering is quite similar, but because there is something in between that is missing in the other response, they look dissimilar to an AI model, and that's why we chose to do only very common headers, because otherwise it would be very diffuse and hard to actually show and represent these partial orderings in our results. So then the question is, okay, we have these features. How can we evaluate if they are useful? And we looked at 2 specific things. First is, how are the features distributed over the data set? Meaning, what we're actually looking for is features that are that show a lot of difference in different HTTP responses. As of course, the more difference, the more information there is for an AI model to actually extract information from. And another thing we looked at was, are there anomalies to be found with the specific feature itself? So are there specific HTTP responses which are very unique, only using this feature? And what can we say about these responses that are very unique? Now Shadi will talk about the implementation of our...
So I tried to divide the implementation into 4 major parts, and I will talk now about the dataset that we used. And the dataset we used is actually a semi-public dataset consisting of HTTP get root scan for the whole IB4 space, and it's about, I think, 52 million row. And it's not really big for big data, but it's 150 giga, the size. And it consists of the IB and a base 64 encoding for the HTTP response. And the provider of this dataset is Rabbit7 Labs. Technologies and the infrastructure that we used is actually we used Pandas, but we also used Dask. And Dask is a Python library that used to do parallel processing on a larger scale datasets, and it allows you also to analyze the data using a cluster of machines instead of one machine, which speed up the analyzing process. And our infrastructure was a group of cluster of 3 machines, about 160 giga RAMs and 60 core CPU. The data processing that we did is actually, we did pre-processing for the data set using a normal Python script, because we needed to decode the base 64 encoding, also to get rid of anything that we will not work on, to make it easier for us to analyze the data. So each row of the original dataset contain, as I explained, of IB and base 64. And then we, as I explained, also we wrote this Python script to only get to discard the body and also the stats line, and only get the headers and the IB. And the result was a JSON file containing only the headers and the IB version for each header, for each response. Sorry. So I give you like a look at how the dataset is looks, and it looks like this. But it was, I thought it's really important that, and also was really important for us that we don't manipulate the data when we decode the basic C4. It was really important to keep the data as it is so that we don't lose the anomalies that we are trying to find. The Dask processing, what we did, the resulting file, the resulting JSON file with the headers and the IB, we transfer it into a Parquet format, and actually to help to reduce first the size of this file on the disk, but also to because Parquet is a binary format, data format, it makes the processing on a cluster of machines really faster. It's really important to note that partitioning the data if you want to work with clusters is really important, because choosing the right partitions of data helps to distribute the load of processing evenly between the cluster of machines. We started to run then a group of queries. This is an example for extracting the headers from the dataset. Using Pandas or using Dask, because Dask, have the similar to Pandas, but it works on multiple machines, on a clusters. As Freek explained, is actually the challenge of our research is because machine learning understand numbers, and we needed to transfer this kind of HTTP responses into numbers. We needed to come up with this kind of features, which is transferring the responses into numbers. And as he explained, we used the uniqueness algorithm. I thought it's also a good idea to put this pseudocode for you guys to show how exactly step by step we calculated the uniqueness feature. It's not really complicated. It's really simple, but it did the job. For the header ordering, it's the same. The only tricky part was to encode each header with a number, and then to store the sequence of numbers, and then to use this sequence of numbers to while analyzing.
Okay, so now to the results. First, before we look at the features, I wanted to show you guys a bit what headers there are in the data set, and these are the most common headers and how frequently they appeared in the data set. So we can see that the connection header is the most common, and then there are 5 headers which are quite common. They are all in more than 80% of the data set. So those were substantially more common than the 6th and on, because those were really in a minority of the HTTP responses. And that is also why, looking at the ordering, we used those 5 responses to prevent having a lot of partial orderings. Now, first we will look at the uniqueness feature. So for the uniqueness feature, I'm showing a probability density function, and this function shows how common specific uniqueness values are. And we can see that there is a normal distribution with one tail, as there's a specific minimal uniqueness that was found in the data set, and which is actually quite common. So there's no tail on the minimal side. And the nice thing about having such a normally distributed feature is that the more uncommon things they get exponentially more uncommon, and this is a feature. This means that this feature can be used by machine learning algorithms, and because it's a linear function, the differences do actually mean more, as a more unique feature can be compared with very ununique features. And there were outliers with very high uniqueness values. So in this graph, we only show until 20, but the highest uniqueness values were actually above 100. And this is caused by maybe by specific web servers or other applications that have a lot of headers which they made up themselves. And the sad thing about this is these anomalies, they don't really correlate with specifically with command and control servers as post exploitation tools. They usually have very short HTTP responses with not a lot of headers. So these anomalies are not really useful for hunting command and control servers themselves. Now for the ordering feature. The ordering feature, it's harder to represent the data in a nice way because there are a lot of partial orderings which are similar, and there's no linear scale on which the orderings can actually be ordered themselves. So I'm showing this table, and you can read it, the number of unique features. It says how many unique features you would need, unique ordering, you would need to represent a part of the data set. So for example, we see that the 4 most common orderings are actually the orderings of 50% of the data set. So there are a few very common orderings, and as you get the orderings get more uncommon, they get very unique. So for example, here at the last part, we see that half of the orderings, in total there are 301 orderings possible. Half of them, in total, they are less than 0.5% of the total data set. So there are a lot of anomalies in these orderings, which we were actually a bit surprised about. So there are specific orderings of only the most common headers, which appear maybe 5 or 10 times total in the data set of 52 million responses. And these orderings that are very unique, they should be investigated further, because orderings of web servers, they are all very similar. And if a command and control server tries to hide by looking like a web server but has these orderings wrong, then they immediately go from being a very common ordering to a very unique ordering, even if you would change one header one place. So that is something that can be very useful in trying to find these command and control servers. So these are actually the most frequent orderings. Let me just grab some water. But so the most frequent ordering has the server first, then content type, content length, date, and connection. And this ordering is in about 20% of the data set. So it's a very common ordering. And the interesting thing about this is this ordering is very highly correlated with a specific web server. It's an Akamai G host server, and Akamai has a content delivery network. So there are a lot of servers from them, and they all have the same ordering of HTTP responses. So if, for example, a command and control server like Cobalt Strike is trying to hide by pretending to be an Akamai G host server, but one of the orderings is switched, so for example the content type is before the server, then that can be picked up by this feature and making the HTTP response immediately very suspicious. And because command and control servers need very specific configurations, it could be that a hacker or pen tester or some attacker doesn't really know the intricate parts of these HTTP responses and the ordering of their headers. So it is quite possible that they mess up this ordering and get caught this way. The last table I will show you is a bit harder to read. So the values, what they mean is how often is the header which is in the column, so in the row, sorry. So how often this connection is in front of this date header. So we see that, for example, the connection header is only in front of the date header in 4.5% of the data set. And in total, we can see that the connection header is usually at the end of the HTTP response, but sometimes the content type is in front of it. And the relations between all these different headers, they are all different, meaning that these specific relations, they could also be picked up by machine learning algorithms. And this shows all these different distributions show that there is maybe more information hidden inside this ordering feature. Okay, so to conclude, our uniqueness feature, the values are very nicely distributed, but the downside is that the specific anomalies that can be found with the uniqueness feature are not really correlated to malicious infrastructure itself. While the ordering feature seems most promising, specifically because these anomalies, they can very likely be command and control servers, as configurations of command and control servers, they might mess up because these orderings, they are intricate, and specific web servers all have specific orderings, and it might be that that an attacker doesn't really know the intricacies of these orderings. And what we think is most promising is combining these features with other information about the HTTP response. So combining knowledge of the ordering with what web server is actually being used, or in case of a command and control server, what they try to look like. And combining this with the other features you could use to find more information about the HTTP response itself. But we still think that endpoint detection, meaning actually looking at the full traffic of a specific host with command and control servers, is still king. That's just because there's a lot more data to look at when looking at full connections, and because you could also use timing and other techniques. And that's of course why we see that intrusion detection systems, they are moving more and more to endpoint detection. But our more passive approach could be used specifically for organizations or government organizations who don't really have access to full networks. So, for example, the organization we worked for, NCSC, in the Netherlands, they are not allowed to even do passive port scanning. Well, as a Dutch citizen, I am allowed to, but the NCSC has more strict rules about it, and that's why they try to use these kinds of passive techniques to still look at these infrastructure and try to secure it try to advise Dutch companies on, okay, you have to look out for these kinds of IP ranges. And what could it mean? So for attackers, you need to be aware of what does the traffic between your command and control server and beacons actually look like. Because it could be that you think, okay, this HTTP response, it's totally normal, there's nothing wrong. But if the headers are in a different order than a normal web server that you're trying to mimic, then that could mean that your operation could blow. And lastly, there needs to be more research to do a full implementation of our features and see if they can actually be used with machine learning algorithms. And that's mainly because there's no data set to use and evaluate these features. So that's one of our main recommendations of future research, that when companies find command and control servers, they save all their data, and they actually collect the traffic between beacons and command and control servers, because this way we have data with where we actually know that they are command and control servers, and this data set can then be used to test these features we created with machine learning algorithms, both clustering and supervised and unsupervised learning algorithms. Because with such a data set, it is also possible to evaluate, okay, which algorithms are actually usable and are the techniques going to work. Lastly, the creation of more features is also an important step, as our features could combine well with specific other features. And well, for this kind of data set, we are the first ones to actually try such things. So our two features are kind of alone in such sense. So more features and and a big data set are the two missing components to actually getting this to work at the moment.
Yeah, but I think this opens the door actually for future research. That we actually start with a big list of features. Like also the body, it can be further studied for other features. For example, the spaces between the tags, because most of these command and control servers, they have the default HTTP or default Apache web page, and that sometimes they miss in the spaces between the tags, or they just use the wrong tag, and then that opens a lot of a new space of discovering more and more features and studying more and more. And I think combining all of these features using machine learning as a tool would be really powerful, at least to reduce the work of an active scanning by double or more or triple.
Exactly. And one last thing that is that could be improved is more collaboration. So this research was actually sparked by the publication of the anomaly of a Cobalt Strike server by Fox IT, which Shadi showed in the beginning. And that's kind of one of the only fingerprinting techniques that was actually published, because a lot of companies, of course, security companies, when they find such an anomaly, they want to keep it, because then they can find the command and control servers in their traffic, while they are scared when they publish it that the exploitation tools, they will patch it and it will go away. While if there's more sharing, then such an open data set can be created, and then it's maybe possible to get the head of the post exploitation tools instead of always being one step behind. So I think
yes,
this is it. Yeah,
this is it. So for the code of and also the process data set, and everything is on our GitLab repo. And thank you.